Welcome to this week's Wednesday webinar. As always, this is being recorded and also live streaming to YouTube, and you can watch previous presentations on our BAA YouTube channel. I have great pleasure in welcoming back Jeremy Shears this week, the director of the BAA Variable Star section, who's going to be giving us a talk on SS Cygni. Thank you, Jeremy.
Excellent. Thanks very much, Andy, for the introduction. And I just want to start off by giving some special thanks and a special vote of thanks to you for all the hard work you've been doing over the last weeks and months in bringing these webinars to us behind the scenes with all the IT. I think this is the 15th BAA webinar, according to the list, since the 1st of April. Pleasure to be here again. So hello, everybody. Welcome again to my observatory in sunny Cheshire. During this webcast, I'm going to focus on one particular variable star. It's actually one of the most loved and certainly one of the best observed variable stars, and it's the dwarf nova SS Cygni. And over the next few minutes, I want to cover a number of different topics. So we'll start off by looking at how SS Cygni was discovered more than a century ago. We'll then look at what a dwarf nova actually is and why it goes into outburst. I'll then move on to considering how we can make observations of the star, how you could go out this evening if you wish to, and if it were clear. It's pretty well placed at the moment, SS Cygni, in the evening sky, and will be over the next few months, well into the new year. And then towards the end, I want to spend a little bit of time looking at some of the unusual behaviour that SS Cygni has been showing over the last few months, and trying to understand what's going on is certainly keeping us on our toes and keeping us guessing. After I've given the presentation, I'm going to be joined by Gary Poyner, and we'll carry out a question and answer session. So don't forget to put any questions in the question and answer box. So Andy, let's move on to the next slide. So SS Cygni was discovered in 1896, and the woman that discovered it was Louisa Wells. She was working at the time at the Harvard College Observatory, and the HCO, as it was known, was one of the prime centres for discovering variable stars at the end of the 19th century and the beginning of the 20th century. And the director of the HCO, Professor Edward Pickering, employed dozens of women over the years to work on the photographic plates taken at the observatory, to identify new variable stars on those plates, and then to classify those stars according to their light curves. And Louisa Wells was one of those women. We can see here in the top left a photograph taken in around 1890 of some of these Harvard computers, as they were called, at work. And many of these actually became famous in their own right as astronomers and made great contribution to astrophysics during the time they spent at Harvard. Just to call out a few of them, if we look towards the back of the room, at the left, you see a woman sitting down holding a magnifying glass, and that's Henrietta Leavitt. And Henrietta Leavitt's work was really focused on Cepheid variables, and she worked out how understanding how these vary, they could enable them to be used as a standard candle for working out cosmic distances. And this period luminosity law that she developed was used a few years later by Edwin Hubble, who worked out by studying Cepheid variables in the Andromeda galaxy that this was this nebula, as it was known at the time, was actually it's an independent galaxy, its own island universe beyond our own Milky Way. If you look at the front, also using a magnifying glass, the woman closest to us, she's examining a plate. That's Annie Junk Cannon, and it was Annie Cannon who developed the Harvard classification system for stars, and that's the basis of the same classification system that we use today, the OBAF GKM system. as I hinted, this became known and is known as the Harvard system, but I think the Cannon system would actually be more appropriate to name it after the discoverer. Call out one more. So standing up at the back is Wilhelmina Fleming. She was also involved in spectral classification of stars, and she was actually the first female computer employed by Pickering. And incidentally, she discovered the Horsehead Nebula by examining Harvard plates. So it's really impossible to underestimate the contribution of these women and many others in our understanding of stellar astrophysics. So let's move on to the next slide. So again, the photo on the left here is clearly taken on the same day, because the women are in essentially the same positions. But there is an appearance in the far corner of Edward Pickering himself. Now, sadly, I don't have a picture of Louisa Wells, at least not one that definitively identifies her. But she would have certainly worked in this room or one of the neighbouring rooms. And her work was to examine hundreds, well, thousands actually, of Harvard plates for the appearance of new stars or changes in the brightness of stars. And this was, we don't have a photo of that definifies Louisa Wells, but she would have worked in that room, and it was she that discovered SS Cygni.
I think we're losing your sound again, Jeremy.
Do speak up if it breaks up again. I think what I was saying on this slide is that Louisa Wells was working on the photographic plates from the Harvard Observatory. She discovered SS Cygni, and that discovery was announced in the Harvard College Observatory publications in 1896. And as was typical in those days, it was announced under the name of her boss, Edward.
Yeah, stop video. We'll see if that does the trick.
Okay, I've just stopped the video.
Okay, let's give that another go then.
Let's see if that works. So yeah, Louisa Wells discovered the star SS Cygni in 1896, and as you can see from the report announcing the discovery, it varied with a period of around 40 days and varied somewhere between magnitude 7.2 and 11.2. And the following year, 1897, the star was given. Louisa Wells.
Jeremy, I think we started to lose your voice again there. So it might be that the two things I can think of is either if you've got a different device like a phone and try joining Zoom on that, or there are telephone numbers you can dial in on Zoom, and I should be able to unmute you as an attendee.
Okay, let's try.
Let's see how this goes.
Yeah, let's see how this goes, and then we can pick up with that one. I'm sure everybody's getting very tired of this particular slide. I certainly am. So I think I was explaining that Louisa Wells discovered the star in 1896. It was officially called SS Cygni in 1897. And I particularly like this picture on the left of the computers at work, because you can see a couple of light curves on the wall. Certainly the one on the left there is the eclipsing binary Beta Aurigae, and there's a date of 1889 on it. So let's move to the next slide. Andy, can you move to the next slide?
Are you seeing, so I've got SS Cygni early years up at the moment.
That's correct, that's come up now. Yep.
Is the audio still okay? Delay on your connection.
Yes. Okay, so SS Cygni was added to the variable star section program in 1904. And one of its most enthusiastic observers, certainly in the earlier years, was my predecessor as director of the variable star section 100 years ago. I think it's fair to say that Charles Lewis Brooke, the director, encouraged lots of observations in these stars, and he even made overtures to the AAVSO, so the American Association of Variable Star Observers, to cooperate on observing the star and to share data. And that was many years before these collaborations became commonplace. You can see some of Charles Brooks's light curves that he drew himself from members' observations in the plot here. What he was aiming to do was to be able to predict the next outburst of stars, and that seemed quite an appropriate thing to be able to do, because many variable stars at the time, like Mira Ceti or Chi Cygni, had relatively stable periods, so you tended to know when they were going to be bright. But even in those early days, it was recognized that the class of stars that SS Cygni belonged to, these dwarf novae, were of a very different type. Not only were their light curves different, but they had peculiar spectra too. And after quite a few years of observing, Brooks found that SS Cygni wasn't going to be quite so compliant as those other variables, and essentially it never kept to the script that the early observers wrote for it. And in a letter to Leon Campbell of the AAVSO in 1921, there's an excerpt from it here. Brooks set down a challenge. He said, "I would offer a prize for a successful prediction of the rise of SS Cygni for, say, a year in advance, if anybody would like to take up the challenge." And I think that being a canny Yorkshireman, he probably knew that his prize was pretty safe. And we now know, with the huge benefit of hindsight, that dwarf novae outbursts aren't predictable. So, and if we can move to the next slide.
Should be up now.
Thanks to, yeah, that's there. Thank you. Thanks to Brooks and many hundreds or thousands of observers around the world, we have pretty much a complete observational record of SS Cygni over the 125 years since its discovery. And none of the well over 1,000 outbursts has been missed in that time. That's quite an observational feat. As you can see in the plot on the left, it's just a snapshot. All you can see is the outbursts. But let's have a look at the larger plot on the right. This is a light curve from the variable star section database, and like all these light curves, you can see the data along the bottom. So these are dates in 2018 and 2019. And on the y-axis, you can see the magnitude. So obviously, the higher up the scale, then the brighter the star is. And you can see that generally the star varies between about 12.2 at minimum and around 8.3 at maximum. And it remains in quiescence, or in minimum, for about, well, something like 75% of the time. And from that low state, it brightens within a few hours, certainly within a day, into an outburst. And typically an outburst will last 1 to 2 weeks, and it'll occur every 7 to 8 weeks on average. If you look at the outbursts in a little bit more detail, they tend to fall into two types. So there's a wide outburst, as one example is shown there, that lasts about 18 days, and a narrow outburst that typically lasts around 8 days. And often these wide and narrow outbursts alternate, but that's not a specific rule. It's a general observation. So we're going to the next slide. So SS Cygni is now known as the archetype of a particular family of dwarf novae that take its name, so the SS Cygni family. But it took many decades of work to really understand what these dwarf novae stars were and how their light curves could be explained. And the unraveling of the underlying astrophysics relied pretty heavily on the vast observational database of observations made by amateurs over the period. And professionals have used those observations to develop and understand the models of these outbursts. So I guess the question is, what's causing the outburst? Why does a star suddenly brighten? Well, in the 1960s, the initial suspicion that these dwarf novae were not single stars but binary stars was confirmed, and that came from spectroscopic observations of SS Cygni. And that was a huge conceptual leap forward. And we now know that SS Cygni comprises two stars. So there's a white dwarf, the star at the top right, and a red dwarf at the bottom left. These stars are very close together. They're about 150,000 kilometers apart. So the double star would fit well within the Earth-Moon orbit. So they're extremely compact. And the red dwarf star is literally whizzing around the white dwarf. It takes about 6.5 days to make an orbit. And because the white dwarf has such a strong gravitational field, it's drawing matter off the red dwarf, and you can see the stream of gas that spirals into this accretion disk around the white dwarf. And sometimes the material builds up in that disk, and there's too much of it, and there's a thermal instability that's triggered. And that thermal instability is what drives the accretion disk into a brighter state. So the outburst that we see is actually the becoming brighter rather than the component stars themselves changing. Move to the next slide. So I think it's worthwhile thinking about why observing dwarf novae in general and SS Cygni in particular is so important. Well, it turns out that accretion and accretion disks are fundamental processes within astrophysics. And studying dwarf novae provides a useful laboratory for understanding how accretion disk physics works. I've got some examples here. So during the formation of an early solar system, a star condenses out of the rotating interstellar gas cloud. The cloud becomes flattened, it becomes a disk-like, and forms what we call a T-Tauri star. And there's a protoplanetary disk that forms, and essentially the planets condense out of that disk. And that's probably how our own solar system formed. On a large scale, accretion disks are also found in galaxies, so they form as disks. Other objects, black holes, supermassive black holes, the intense gravitational field around the black hole causes an accretion disk to be formed, and many other objects. So studying accretion disks in black holes and studying the accretion in the early solar system is really difficult, or actually impossible in the case of the early solar system. So dwarf novae provide a proxy for gaining information about what's going on in accretion disks. Let's go to the next slide. Thank you. So our understanding of accretion disks was actually recently challenged quite severely by another fundamental ingredient in astronomy, and that is distance measurements. The distance to SS Cygni was measured a few years ago by the Hubble Space Telescope, and it turned out to be far too large to be supporting the standard accretion disk theory. And people began to ask whether these models were wrong and should be thrown out. The Hubble Space Telescope data actually suggested that SS Cygni should be permanently an outburst, and clearly that's not what the observational data showed. So people began to be suspicious about those measurements. And it was observations by a team led by a good friend of the variable star section, Professor Christian Koeniger from Southampton University, who showed that the Hubble Space Telescope measurements were actually wrong. instead, the SS Cygni was actually as far away as it was supposed to be to support the models. And I can assure you that came as something of quite a relief to the astronomical community. And Christian Knigger's paper in the Science Journal described how the team relied on observations of SS Cygni by amateur astronomers to trigger their radio measurements. So move on to the next slide. Time to talk about how to observe SS Cygni. If you have a small telescope, it's actually a very rewarding variable to watch. If you have something like a 6-inch telescope, you can easily see the complete range of the star. And finding it isn't too difficult. It may take you a few attempts the first time you try and track it down, but after you've found it a couple of times, it becomes routine. It's also circumpolar, so you can observe it any season, although of course it's well placed during the summer and autumn, which is why I'm suggesting start to observe it now. So this chart here shows what the sky would look like if you went out at around midnight tonight, BST. If you look to the southeast, you'll find the well-known summer triangle comprising the three bright stars of Vega, Altair, and Deneb. Deneb, of course, is the brightest star in Cygnus, the Swan. And SS Cygni lies roughly 10 degrees below Deneb and a little bit to the left. So if we move to the next slide, we can look in a little bit more detail at the field that surrounds SS Cygni. So here we can see the coloured chart. That's showing the area around Deneb. And one popular way of finding SS Cygni is to locate Rho Cygni. You can see it well to the left of Deneb in the little chart there. And there's a row of stars that Rho Cygni is part of that leads down to the star 75 Cygni, which is marked there. That's a 5th magnitude star, so it's just about visible to the naked eye from a dark site. Then if you look at the enlarged circle, you can see the area around 75 Cygni, and SS Cygni lies to the left. And it lies on the edge of a small triangle of stars. Now, if you look at the chart on the right, this is a variable star section star chart of the 1 degree field that SS Cygni sits in. You'll see SS Cygni in the center. Like all variable star charts, the variable is marked with a little dot with a circle around it. And you can see the triangle of stars that I was referring to. Note this is an inverted field, so this is how you would see it through an astronomical telescope without a diagonal prism. So you can see that the SS Cygni lies between the stars B and E, and when it's in outburst, it'll get about as bright as star B. And the aim is to compare the brightness of the star with others in the field, and the magnitudes of those others are shown at the bottom of the chart. At the moment, observers are reporting it at around magnitude 11.4, so it's near quiescence. How often should you observe it? Well, because it's somewhat unpredictable in behaviour, recommended to observe once every clear night. But if it's active, if it's brightening, or if it's fading, several times a night is also good. And if you can time the observations to the nearest minute, that will be excellent. So these charts are available from the Variable Star section website. So if we go to the next slide, there's a series of images here taken by Mike Harlow showing SS Cygni in an outburst last summer, so in August of last year. So if we look at the top image that Mike's taken, you can see the star marked there with the two little lines at around 12th magnitude on August the 13th. The light curve on the right shows the time at which these observations were made. So this first observation on the 13th was made, as you can see by the first arrow, when the star was in quiescence. It was faint. 6 days later, on the 19th, it had brightened considerably to around magnitude 8.7. You can see it a lot brighter in the image, and you can see it's near the maximum of its outburst, shown by the arrow. And then on the 29th of August, the star was fading considerably. It had already gone down to about magnitude 9.5 at that time. And it wasn't until I was examining Mike's great images in more detail that I noticed for the first time that there are 3 very faint galaxies to the left of the field. I don't know if you can make them out. I can certainly see them on my screen. And this came as quite a surprise to me, because SS Cygni lies, of course, in the Milky Way, and yet there are galaxies there. So I have to say there's something in this field, even for the deep sky observers. Let's move on to the next slide. Let's consider what SS Cygni has been doing lately. So if I've given the impression that everything is known about SS Cygni, I've not done my job correctly, because that'd be quite a wrong conclusion to make. Because from time to time it does do odd things, and I think that's what makes it a really interesting star to follow. I mean, many years ago, not long after it was discovered in the early 1900s, it ceased to exhibit outbursts altogether, and only underwent relatively minor fluctuations. And it seems to be behaving somewhat unusually at the moment. And I want to turn to this anomalous behaviour, and perhaps encourage you to observe the star yourself to try and understand what's going on. So there's a light curve here from the beginning of last year, so the beginning of 2019, until actually last night. The star was last in outburst in the middle of June. You can see the outburst on the right there. And at first glance, that light curve looks particularly looks like any other part of SS Cygni's light curve. It's nothing particularly noteworthy there. But let's have a look in a little bit more detail. Because if we look starting last September, you can see some strange outbursts. So the first arrow shows an outburst in September 2019. That's a short outburst, but a normal short outburst. There was again, that was followed by a slightly fainter outburst, but an unusually faint outburst that's a little bit broader. Then the third outburst, so the one that followed that, was essentially a mini outburst. It's actually a little bit difficult to make out in that light curve, but there was a small outburst, and that was followed by an unusually broad outburst. So the fourth outburst, the fourth arrow indicates this is a very broad outburst, and that occurred at around the turn of the year, so 1st of January 2020. If that weren't enough, so that is unusual behaviour. But then it went for about a month during February and March, when it was in quiescence for most of the time, and it's since shown 3 more outbursts. But there's also something else that's strange going on. That's if you look at the quiescence over the last few months. That period in February and March when it was in quiescence, it was actually not as faint as it would normally be. Remember, it's normally around 12.2 in quiescence. Well, this is around 11.5. And if you look back to the earlier part of last year, you could also see that the quiescence was also not as faint as you might expect it to be based on its historical record. So this is clearly not normal behaviour for SS Cygni. And there's been further unusual behaviour reported. So last month there was a report in the Astronomer's Telegram from you had the right slide there, Andy. I've gone on to the next slide, thank you. SS Cygni brightening in X-rays, because this team at Tokyo University found that it was actually brighter in X-rays than normal, They followed the star using the Neutron Star Interior Composition Explorer mission instrument, and that also showed that the star was behaving quite violently and varying quite rapidly on X-ray timescales of a few seconds. Another team of Japanese amateur astronomers also found unusual variations in the optical light curve. During two of the recent outbursts, they found random brightness variations are much bigger than normal, so around 0.1 to 0.3 magnitudes over a period of an hour. So no definitive period, it was random, but roughly an hour. And that's certainly larger than variations that have been seen in the past. So I think we need further observations to understand what's going on. And it's fair to say that SS Cygni only reveals its secrets rather slowly. And very often, breakthroughs in the understanding of the star occur when we combine observations at different wavelengths. For example, there were radio observations made in 2016 of giant flares that were observed and reported in this paper on the bottom right in the monthly notices. And that was a team led by astronomers at Oxford. And they correlated optical variations, including diameters, with their own radio observations. And they've speculated that the variations might be caused by jets of synchrotron radiation being emitted by the poles of the white dwarf. And it's only recently that jets from dwarf novae have been observed. They're well known in black holes and in quasars and other objects, but only recently in dwarf novae. So again, another reason for keeping the star under observation. Let's move to the next slide, Andy. This is actually my last slide. So in spite of the technical difficulties that we've had, I hope you've enjoyed hearing a little bit about SS Cygni, and perhaps you've been encouraged to observe the star maybe tonight, in the next few nights, and continue observing over the next few months until the end of the year. As I said earlier, it's in range of a small telescope. You can also monitor it by CCD observing as well, and even time series observing by CCD cameras could be very interesting, especially in view of the observations reported by Japanese CCD observers in recent outbursts. And I think one of the fascinations for me around dwarf novae is that these variations can occur on lots of different timescales. So we've seen the 125-year light curve, we've seen the outbursts around 40 days, we've seen these last a few days, they rise from quiescence into outbursts within a few hours. And even within a few hours, every few minutes, there's some other variation, often a random variation going on. So yeah, for me, it's incredible to be able to go out into your back garden at night, point your telescope at SS Cygni or any other dwarf novae and see some high-energy astrophysics in operation. So I'm going to stop there. Thank you for listening. I'm now going to open for the question and answers, and hopefully Gary is going to be able to join us for this. So I'd like to welcome Gary Poyner, who is one of the world's preeminent visual observers of dwarf novae. And Andy, have we got Gary on the line?
Yes, Gary's on, and I promoted him to presenter. So Gary, what I'm going to do is I'm going to unmute you from this end, unless you want to unmute yourself. And we have been getting some questions in, and just to let everyone know again, just to avoid any confusion, if you want to ask a question, if you move your mouse around and go to the bottom of your Zoom screen, or at least it's the bottom of most people's screen, around in the middle, you'll see a Q&A button. If you click that, you'll be able to type any questions which you want to ask. And I'll read them out, as that's probably going to be the easiest way to do this.
So Gary, can we hear your voice? Are you there?
Yeah, I'm here. Good evening, everyone. Yeah.
Hey, welcome. Thanks for joining, Gary. Just out of interest, when did you start observing SS Cygni?
1975, September. Long time ago.
Pretty precise.
Yeah.
I talked about using different kinds of telescopes, even relatively small ones. What have you used over the years to observe it? I see with your picture online now is a huge telescope, but I think you've used other smaller ones as well.
Yeah, I mean, in 1975, I was using just a standard 6-inch f8. But the thing is, because it's so bright, I mean, it gets at minimum its magnitude 12. So you only need a smallish telescope, 6 or 8-inch telescope, to see the whole pattern of SS Cygni. I wouldn't use a 20-inch telescope on SS Cygni at all. But certainly the best thing I've ever used to see SS Cygni in outburst is a pair of 10 by 50 binoculars. And the very fact that you can see an accretion disk with a pair of 10 by 50 binoculars never ceases to amaze me.
Yeah, that is indeed pretty impressive. Yeah.
Our first question is from Jack. Hello, Jack, and I think this may have been answered during the presentation. This was typed in fairly early on, and it says, what is the magnitude of SSC?
Yeah, so it varies between, I don't know if you can go to one of the light curves, Andy, but you can see it's varying between around 8.2 and 12.2. So 8.2 at its brightest and around 12.2 when it's in quiescence at minimum. But as I was explaining, at the moment it seems to have thrown the rule book out the window, and its minima are actually brighter than 12th magnitude. And Gary, do you recall any other time? Do you recall any times in your observing history when it's been showing these brighter quiescence periods?
Yeah, there's been a few times. I made some notes earlier. 1982 was a period. 1993 and 2008 were 3 of the recent ones. Certainly, I remember that. And it's usually when this anomalous outburst activity begins, something unusual has happened, either 1 or 2 outbursts previous to that. So if you see something unusual happen, then you know that something might happen at the next outburst, or there might even be an outburst missed. So we might go 80 days before the next outburst rather than 40.
Yep. Very good.
I'd also just add as well, we've got just over 100 people with us this evening from across Zoom and YouTube. So in spite of the glitches we had with the technology, numbers have held up well. Next,
thanks for persevering, everybody.
Next, we have another question from Jack, which was during the presentation, which was, I assume Louisa Wells is on that pic.
Yeah, so unfortunately, I don't know. So there were more than 80 women computers that Pickering employed over the years, and some of them were only there for a few months or a few years. Others were there for decades. I haven't found a record about how long Louisa Wells was there. And neither have I found a photograph that positively identifies her. So whether she's in that picture or not, I don't know. There are many other pictures that I've also looked through in the archives, but none of them identify Louisa Wells. Whilst we're on that photo, it's also worth mentioning the women and EC Pickering in the room there. It's clearly a posed photograph. Obviously not respecting social distancing, and descriptions of how they observed at the time indicate that they never crammed into a room like that. There were several rooms, and they spread themselves out. So that was clearly posed for these photographs.
Next, I'm going to put in a couple of questions together from Malcolm Porter, because I think they're basically along the same sort of thing, just expanding on it. So it's thinking about a toy gyroscope. Can an accretion disk precess, and does this precession show itself as a signal in the light curve?
Yes, it can do. So there is a particular class of dwarf novae, and the archetype of that class is SU Ursa Majoris. And what happens here is that the accretion disk, for one reason or another I won't go into, actually becomes elliptical. And when it becomes elliptical, that processes, and it processes with a period slightly longer than the orbital period of the secondary star, and it shows itself as a modulation in the light curve. And the modulation is often easily to pick up in amateur telescopes. It's typically about 0.1 magnitude modulation, could be even up to 0.3, 0.4 magnitudes. And those are called super humps. And they are very useful because they give an indication about the orbital period of the secondary star around the white dwarf. So precession is possible.
Next is a question from Richard Bottle. Why did Hubble get the distance to SS Cygni wrong? I guess I'm meaning the Hubble Space Telescope.
I think it got a lot of distances wrong. I think the data weren't of sufficient quality at the time. So it's only with other more refined measurements that we became to know what the distance was, and I think Gaia will be providing even more accurate distances. I haven't actually seen any Gaia measurements to SS Cygni. Actually, Andy, you work on Gaia. Have you seen any measurements released yet on SS Cygni's distance?
It's probably already out there. What I'm not sure is whether it will be reliable or not. With the data release 2 of Hubble, which we have at the moment, the distances to double star systems are unreliable because it assumes a single star model. At the same time, the distance between the two components, SS Cygni, is probably well below the visibility. So it might be it has a reliable distance. If not, then I think in a few months' time, DR3 of Gaia is coming out, which will be a significant improvement.
I must say it'd be slightly awkward if it confirms the Hubble measurements, wouldn't it?
Yes. So on to the next one is a question from Simon Street. What is the regular pattern in the light curve that spans many decades in an early slide?
Oh, that's the compilation slide, isn't it? I think that's yeah. So the regular pattern. I wonder what you mean by the regular pattern. Is that simply the year numbers that are written? The years
so
are written.
If I use the mouse, I'll show you the kind of year numbers go along there. Yeah. Otherwise, you have the outbursts, which kind of appear at a sort of semi-regular interval.
That's right. So the year numbers are not part of the signal. That's just where they've been placed on the plot. I don't know if that answers your question. On average, there's an outburst every 40 days or so. But even but glancing at this, you can see there's quite a variation in that long light curve.
We've got a thank you for the presentation from Thomas, and he's just wondering if there are recent spectroscopic observations. Would it be suitable for an Alpi spectroscope or needs high resolution?
I'm probably going to turn this one to you in a moment, Andy, about the type of spectroscope you can use. But yes, it is bright enough for amateur spectroscopists. And I know David Boyd has done some work on this in recent years. He wrote an article, I think it's probably about 3 years ago in the BAA journal where he studied this. Andy, with that particular model, do you think it's possible? I'm not familiar with the model.
Yes, I mean, basically what the issue you have with spectroscopy is for low resolution spectrographs, you can go low, but as you go to high resolution spectrographs, because it spreads the light out, it makes it much more difficult to go faint. So with something like an L high res 3, which is one of the other common types of spectrograph, which is quite high resolution, it spreads the light out so much that you only really get good spectra of about sort of 6th, 7th, maybe 8th magnitude. You can occasionally go fainter to sort of 10th magnitude, even 12th, but the spectra becomes very noisy, or you have to have incredibly long integrations. And just having a quick look in the BAA Spectroscopy Database whilst we're on, and I can see we have lots of, actually I'll just change my share for a minute and I can switch over to here. So here's the BAA Spectroscopy Database. I've just done a quick, this is available online, we've just done a quick query on SS Cygni. You can see there's lots of spectra in there at varying levels. So most of these, the resolution is this column. So kind of 490 is around the resolution of, say, an LP, getting up to 800, 1,000, those will be more likely ELISA, and then 15,000, that's more like an L-high-res 3. So if I do a plot, I'll see if that actually, I'm not certain if that will show up on the, hopefully you'll see that, but there's a spectrum of SS Cygni, and that's a kind of reasonably low resolution one. And if I click on a high resolution spectrum, say this one, hopefully you'll see, then you'll see, yeah, a lot of this stuff here, that's just noise in the spectrum, but you can see one of the lines comes up. I don't know, are you seeing those?
Oh yeah, I can see those.
Great, that works. What I'll do is I'll switch back to the presentation in case there's anything else we want from there.
So Thomas, thanks for the question. Do have a look in the spectroscopy database and see what you can make of it. It's accessible to everybody. You don't need to log in to be able to be able to view spectra.
And what we actually, it's probably worth as well just mentioning that both the spectroscopy database and the BAA photometry database, which is the previously was the variable star section database, are both accessible from the BAA homepage. So I'll just quickly flick back over to the browser again. So here we are on the BAA homepage, and then down the right hand side we have all the sections here, and then there's a link to photometry database and spectroscopy database. So photometry database, that has all the observations of SS Cygni, which have been reported to the variable star section. You kind of go in and you click SS Cygni, apply filter, then you can do a light curve or a data table. There'll be absolutely masses of observations of SS Cygni, so hopefully it won't break things if I try and do one now, but it's, yeah, you can see if you just do it all in one go, it just becomes, you can't, it's a bit unusable at that sort of level. So you kind of need to sort of filter it down in date.
Okay.
Next question is from Andrew Dumbleton, sorry. Are there other dwarf nova misbehaving in similar manner to SS Cygni?
Gosh, well, there is a dwarf nova that's doing some very interesting things. Whether it's misbehaving or not, I don't know, but certainly worth talking about. There's a dwarf nova that's in outbursts at the moment called PQ Andromedy, and I know that's something that a star that Gary's been following for the last month, because it's undergoing a very rare outburst. Gary, do you want to give us an update on what it's up to, and perhaps when it was last observed?
Yeah, sure, Jeremy. Good evening, Andrew. I think that's Andrew Dumbleton I know. Thank you for a very awkward question.
Ah, yes.
Okay, so PQ And was originally thought to be a nova way back 30 years ago. And it went into outburst again in March of this year, March the 28th. A Japanese chap, Kenji Hirasawa, discovered it at magnitude 10.5. And since then, it's still visible in the morning sky, but its behaving now is completely different to how it behaved when it was first detected as a nova 30 years ago. It's faded once to about magnitude 16.5, but since then it's had 2 rebrightenings up to about magnitude 13.5. So it's an incredibly interesting object to observe. One of the problems with this outburst is the fact that not many CCD observers have managed to get detailed CCD photometry of it, because obviously with its position in the sky and the outburst occurring in the summer, there hasn't been that long for observers to take observations of the star before the sun rises. So hopefully, as we move into July and August, more observers with CCDs will be looking at PQAnd and hopefully get some time series photometry. So that's a variable star which has certainly shocked the entire amateur community by an outburst. But Andrew, I think Andrew was talking about other types of dwarf nova, and yes, the SU Yuma has missed several outbursts. It's kind of over 100 days without showing an outburst before it went into outburst 4 or 5 nights ago. So these things often do things like this. And I often find that it's better to approach a dwarf nova than not to expect it to do what you expect it to do. We'll always expect the unexpected, and then you won't be too surprised when something unusual happens.
Very good. Thanks, Gary.
And the next question we have is from Stuart Coulter, who's actually giving the webinar next Wednesday, which is on Cook, the transit of Venus, aftermath and legacy. And Stuart's question is,
excellent.
How exactly do you measure magnitude? Is it comparison stars or technology? And if so, how reliable is that?
Okay, so the answer to that depends on how you make the observation. So if you make it visually, I'll ask Gary to speak about that in a moment. If you make the observation using, say, a CCD camera, then it's you might describe it as technological. It's simply a matter of taking an image of the field where the star lies, in this case SS Cygni, and then importing that image into a software package that enables you to do photometry, and there are a few of those available. There's AIP for Win, astronomical imaging processing for Windows, and there's Astro Image J, and a whole host of other ones. And within that, it's a relatively simple mechanism where you tell the program which is the variable star by clicking on it, and you tell it a comparison star by clicking on that. And the comparison star from a database will have its magnitude precisely described. And from the difference, you can then, in brightness that the program measures, you can work out the brightness or the magnitude of SS Cygni. And depending on your experimental setup, the exposure, the size of the telescope, and your integration time, you can get accuracy down to a few thousandths of a magnitude if you're very, very careful. So that's a CCD or electronic observation. For visual, it's different. So Gary, would you like to give a description of that?
Yeah, sure. Well, Andy, if you could bring up Jeremy's slide where it showed the chart for SS Cygni, that might be a help.
That's a good idea.
That's it. Yeah, okay. So on the right there, you can see there's a chart. And on the chart, there are stars which are lettered. Those stars have accurately, well, we hope they are, accurately measured magnitudes. Now, the object of the exercise is that when you look at a variable through a telescope or binoculars, you choose 2 stars, one slightly brighter than the variable and one slightly fainter. The difference in magnitude between the 2 stars shouldn't be more than about 0.5 or 0.6. And you can see on the bottom of the chart that you have the magnitudes there, so you can judge what the difference is between the 2 comparisons. And then it's a simple, well, I say simple, it's a simple exercise then to place the variable in between the 2 stars. You can either measure it as a fraction of the difference of the 2, or if the more experienced you get, you tend to recognize differences of up to 1/10 of a magnitude. So then you can make an estimate of the variable's brightness, write that down in your logbook. And then you might think, okay, you know, how accurate I am. Well, what you do, you go to the BAA VSS database and you check observations of the star made on the same time that you've made yours. And then you can have a good idea of how good you are making an estimate. When you first do this, you might be within 0.4, 0.5 of magnitude of other observers. But once you've done it 40 or 50 times, you realise how simple it is to do this. And you can get within a tenth of a magnitude accuracy between experienced observers. Not as good as CCDs, of course, but some people might argue that observing visually is more fun. But that's another story.
Yeah, I'd certainly say
that's one for a few beers, I think, Gary.
Yeah, absolutely. Yeah.
I've done CCD and visual observing, and yeah, I think that they can both be fun, but sometimes just be able to sort of go out with a pair of binoculars or something like that is kind of nice and easy going, and you can kind of take it fair, have a relaxed and fun time.
I think that's right, and I think that's a way that people often get into variable star observing. So they have other programs, maybe they observe planets or deep sky objects, and then they decide to take one variable star and then follow that as part of their other observing programs and just look at it from time to time, and then some of those then get hooked on it. So yeah, starting easily, starting leisurely is a good way to proceed.
We've got next question in from Simon M. Is the variability caused by the rotation with one star blocking the other, and how can the inclination be determined accurately? For example, is it 50 degrees when studying the shape of the charts? Okay,
so in the case of tonight's star, SS Cygni, so the variation or these outbursts is not caused by one star blocking the other. The variation isn't actually caused by the stars themselves. It's this accretion disk around the white dwarf that brightens. So neither the stars remain the same brightness, but the accretion disk brightens. Now there are other dwarf novae where they're very similar. So you have a white dwarf with a red dwarf going around it, and because of their orientation in space, we see them in the same plane, and there you can get eclipses. So one star does block the other one. So the red dwarf blocks the white dwarf, or more commonly, the red dwarf blocks the accretion disk around the white dwarf, and then you can get some really deep eclipses. Some of these could be 3 magnitudes in depth if it's a full-on eclipse of the accretion disk. You can work out the angle of orientation from spectroscopic observations, or at least professionals can do that.
And next was just from Simon Street to say, yes, he can now see the numbers. So that was about the periodicity.
Excellent. Oh, good, Simon. Yeah, thank you. Pleased with that, Simon. Yeah.
And we have a thank you from Thomas for showing the database. That's good. Thank you, Thomas. And then,
yes, and he's going to have a look as well. So yeah, do have a look, Thomas. That'd be excellent.
Jack then has a question, which are there any particular spectral lines of interest, for example, H alpha?
Yeah, I think H alpha is the one that people primarily observe. Any other thoughts on that?
No, I was just taking a quick look. I mean, H alpha is in emission, and there are some other lines. I expect there must be a significant change in the spectrum over the course of outbursts, but it's not an area where I have expertise. And I think the real trick with spectroscopy as well is, particularly if you're going to look at a particular line, is knowing which lines are useful for diagnostics on the system. And that often takes a little bit of research to find out, perhaps sort of looking at some professional papers to see who's done some research on it, to see what are the most interesting lines to look at.
Yep.
We have a question from Malcolm Porter. Does the brightness variation depend primarily on the rate of flow of gas onto the accretion disk, or on the behaviour of the disk?
If I understand the question correctly, it's both. So the brightening occurs when there's a lot of material in the disk, when it builds up in the disk, and then it'll flip into this hotter, brighter state. but the time interval between each outburst does vary depending on the rate of flow of material from the red dwarf into the accretion disk. That is fairly constant, but not completely constant, and is an active area of astrophysical research. So the first thing to say is that the accretion flow in some dwarf novae is actually quite blobby. So you get a sort of stochastic variation as the material flows into the disk. But the rate of flow can be affected by other things. And one of the active research areas is how star spots on the secondary, on the red dwarf, can affect the flow of material. Because if you remember the picture of the accretion flow off the red dwarf, if a star spot rotates under that, it can block that flow of material. And it can completely cut it off in certain dwarf novae. And then the accretion disk shrinks, becomes very small, and the star becomes very faint. So star spots are causing the variation. There are various other things. The irradiation of the red dwarf by radiation from either the white dwarf or the accretion disk can affect how much material is released by the red dwarf. So lots of different physical processes going on, and again, another reason why it's so interesting to follow dwarf novae.
And I can add just a little bit on that, because that's to do with some of the research I've done, is with star spots and SS Cygni, they're detectable using spectroscopy. You do need very large telescopes to get a higher signal in there, but because the star spot is at a lower temperature by several thousand degrees, the spectrum is of a different spectral type. And so what you start seeing is titanium oxide in the spectrum of SS Cygni.
Okay.
Next one is from Paul, and this is: to what extent do observations made over 100 years ago, or even 30 years ago, differ from those made now, given differences and improvements in equipment, as well as other factors such as light pollution? How comparable, accurate is the data from different eras?
Okay, Gary, I don't know what you think about this one. I mean, you disclosed earlier that you've been following this star for about 45 years.
Yep.
So
I think the big.
I think the observations. Yeah, go on.
Yeah, I think the big thing about this is the accuracy of the comparison stars. 45 years ago, even 25 years ago, you would get two sets of charts, one from the BAA, one from the AA VSO, and maybe the comparison stars weren't exactly the same magnitude, even though we were choosing the same stars for each chart. Nowadays, with our sophisticated measuring devices, I think the accuracy of the comparison stars means that today's data is as accurate as it's ever been. If you go back 100 years, the observers, they're wonderful observers, wonderful visual observers. They're only able to make the comparison using the tools that they had at the time. So you can look back and you think, okay, perhaps that magnitude is a little bit off, or maybe that reduced magnitude is a little bit off. But it's not the observers, it's down to the accuracy of the comparison stars. And I think we're very close to making that sort of foolproof now. I don't think we have to worry too much about comparison star magnitudes, certainly visually. There's always room for improvement for CCD observers, but for visually, a tenth of a magnitude, I think we've pretty much got that cracked.
And it's also worth noting that one of the areas which in particular the BAA variable star section has put in effort is with old charts compared to new charts. If you're able to tell which stars were used, and if the observers submit their full what's termed a light estimate, where you know what comparison stars were used and how much of a difference was, it's possible to recalculate an estimate from 50 or 100 years ago using the modern, more accurate magnitudes for those comparison stars.
Yeah, that's very easily done now. It's you can run it through a computer and it could do thousands of observations in a very short time. So it's very important for anybody new listening to this that's going to go out tonight and look at SS Cygni is to always mark the comparison stars that you use and do a light estimate.
Good points. I think the other thing to be aware of in looking at very old observations, you may remember that when I showed the paper, the discovery paper at the beginning of the talk, the variation was given between magnitude 7.2 and I think 11.2. So that sounds very bright compared with now. In fact, we don't think it was different then. It's just that those were photographic magnitudes, and the plates that the Harvard Observatory was using at the time had a particular spectral response, which is different from our eyes. And I think people have done quite a bit of work to cross-correlate and to be able to make the necessary modifications.
The last question which we have is from Andy Pryor, and this is, has anyone input the time series brightness data into a machine learning algorithm to see if it can come up with a prediction?
Well, not that I'm aware of, but perhaps they have. I think the challenge might be that some of these variations are indeed random or stochastic. So I don't know whether machine learning will help with that, but I don't know. Maybe there's a PhD project in that for somebody.
I think the other thing is with machine learning, it doesn't always tell you the mechanism, or it doesn't in itself tell you the mechanism or why it's varying. So it might be able to predict in the best case scenario what's happening. But if it doesn't lead to understanding why it's happening, then it there's still research to be done. I'll just check to see if we've got any questions come up on YouTube. Nothing there. I do see Simon M has his hand up. If there's a question you'd like to ask Simon, are you able to type it into Q&A? If not, I'd like to thank Jeremy once again for persevering to get the sound issue working, so able to hear this fascinating talk, and also to Gary for joining us in the Q&A to help make this an informative and fascinating session.
Thank you very much.
Thank you, Andy. Well done.
Thanks.
Yeah, thanks for joining, Gary.
Cheers, Jeremy.
And just to let you know about what we have coming up, again, as I briefly mentioned earlier, this Saturday we have the BAA summer webinar with 11 o'clock on Aurora, Steve and Noctilucent Clouds by Sandra Brantingham, and at 2:30, latest news in spacecraft exploration of comets and asteroids by Dr. Colin Snodgrass. And then next Wednesday we have Cook, the Transit of Venus, Aftermath and Legacy by Stuart Coulter. Thanks again for joining. Bye.
Thank you.